This is going to be our lecture video for April 1st. I'm going to be talking about graphing some trig functions today. Starting off with some warm-up questions. The first is, are the angles 585 and negative 495 coterminal? And can we prove that mathematically? So if they are coterminal, that means that when graphed in standard position, they would have the same terminal side. But there's a little bit of algebra you can do here to prove that two things are coterminal. What you want to do is find the difference of angle 1 and angle 2. So do angle 1 minus angle 2, and then you want to divide that by some amount of full rotation. So either 360 degrees or 2 pi, depending on what unit your problem is in. All right, and so that means that the difference will give you the angle between these two terminal sides. And if that angle is a multiple of some number of full rotations, then they are coterminal. So you're going to do this. This is going to give you some number. We'll just do a number sign. All right. If this is an integer, they are coterminal. If this is an integer, the angles are coterminal. All right. So let's check with these two. And it actually doesn't matter which order you do it in. I'm going to do the bigger minus the smaller. 585 minus a negative 495. Let's see what that is. So 585 plus 495 equals 1080. I'm going to divide that by 360, and I get exactly 3. So not only are they coterminal because I did get an integer, I now know that they are separated by exactly 3 revolutions. So we'll just say yes, coterminal. All right, what about these two? Well, these are given in radians. So I'm going to do a very similar formula, angle 1 minus angle 2, but this time divide by 2 pi. If they're separated by 2 pi, if we get an integer, then they must be coterminal. So let's see, I've got 5 pi over 6 minus a negative 19 pi over 6 all over 2 pi. And these have a common denominator so they can be combined. The minus and negative becomes a plus, so this becomes a 24 pi over 6, all divided by 2 pi. I'm going to make that a 2 pi over 1 so that I can copy dot flop this and make this 24 pi over 6 times 1 over 2 pi. Now the pi's can cancel out, and I can multiply straight across the top and straight across the bottom to get 24 over 12, which equals 2. So they're separated by exactly 2 revolutions, and yes, these are coterminal as well. All right, so to recap, take the difference, divide by either 360 degrees or 2 pi radians. If you get an integer, they are coterminal. If you get a decimal, even if it's like 3.5, they're not coterminal. All right, goal. To explore how trig graphs can be shifted. Why are we doing this? So we can change an equation to fit periodic data. Generally, that's kind of our goal in the end of a lot of this, is to be able to fit data and describe the world around us with these functions. All right. So if you haven't, get your notes out, put today's date, and copy down the standard form of a trig graph. Y equals a times sine of bx minus h plus k. Now, this would be the standard form of a sine wave. This could also be cosine or tangent there. All right, and then x, we sometimes use x as an input, but theta is also common here. Because our input is specifically an angle, sometimes we use theta as the variable when our input is going to be an angle. So yeah, that's the Greek letter theta. So sometimes you'll see it with a theta there for x. And the one thing I want to point out is A here stands for amplitude. So whatever number we see at the front there, if we don't see a number, we'll assume it's a 1, and the amplitude of that sine wave will be 1. But if we see like a 4 here, it means the amplitude is 4. I'll also point out K is the vertical shift. And the easiest way to think about vertical shift is shifting the midline up or down, and then kind of everything comes with it. But H is not horizontal shift. This is kind of where it breaks a little bit. So let's not label that yet. Let's just label amplitude, vertical shift. Sine could also be cosine or tangent, and X is sometimes theta. Okay, so horizontal shift, when we're dealing with periodic functions, we're going to start calling it phase shift, because horizontal shift doesn't make as much sense with periodic functions. You can shift a function far enough that it syncs up with itself again. The peak that was over to the left is now covering the peak to the right. And so phase shift is a better word for what's happening here, to describe how the wave has changed. Certain peaks have moved to different spots, and you might not even be able to tell where a certain peak came from. So we just call it phase shift. There is a formula for phase shift. Looking at standard form, you can always get phase shift by h over b. Right here, h over b. All right, so here I've got a trig function in standard form. Pause the video, copy it down. Let's find the phase shift. So one thing is we don't bring the negative with h. So h here just equals 8, and b equals 4. And then we do h over b equals 8 over 4 equals 2. So wherever this function was before this h value was added in, and this b value, everything is going to be moved 2 units right. Or we just say a positive 2. Okay. I think that's that for phase shift. Let's talk about period change. So if our data is oscillating more frequently than every 2 pi, we can change the waves to oscillate more frequently. Here we see in blue is just y equals sine of x, oscillating every 2 pi radians. But if I put a 2 in for b, now it oscillates every pi radians. You can see the period went from 2 pi to pi. We make one full cycle by the time we get here. So there's a formula for this as well. To get the period of a function, you do 2 pi divided by b. At least that works for sine and cosine. Tangent's a little bit different because it's got a more frequent period. The frequency of a tangent wave is every pi, so you just do pi over b. So this is sort of like original frequency divided by b. All right, so here I've got a function, y equals the cosine of 6 pi x. It's really common to have pi in the b value, because then it'll cancel out this b and it'll turn the period into some much more recognizable number, a rational number. So here our b value is 6 pi. So 2 pi over b becomes 2 pi over 6 pi. The pi's cancel out. 2 over 6 implies to be 1/3. So what we can say is that this wave oscillates every 1/3 unit on the x-axis. Did I spell oscillates right? Oscillates. Nope, two L's. Oscillates. All right. This wave oscillates every 1/3 unit on the y-axis. All right. So just sort of to build some intuition about this, bigger numbers here cause us to oscillate more frequently, so we get smaller periods. So instead of going big, well spread out waves, it's like going like this. Many more cycles per unit distance on the x-axis. All right, range. So range describes the possible outputs. It's normally, with no shift, it's the interval from -1 to 1. So -1 is less than or equal to y is less than or equal to 1. All right, two things can change this: the amplitude and the k value. So if I shift everything 4 units up, I need to shift these boundaries up 4 as well. And if I stretch everything out by 5, I need to stretch these out by 5 as well. So we can use a little bit of a formula here, although I don't like us to memorize this formula. A minus k is less than or equal to y is less than or equal to a plus k. So the amplitude minus any shift, amplitude plus any shift gives us our interval. But I'd rather just think about it intuitively. So this 5 here is going to shift it from just going oscillating between 1 and -1 to oscillating between 5 and -5. So that's just y equals sine x. Y equals 5 sine x. And then when we shift everything up 4, all of these shift up 4, and we get y equals 5 sine x plus 4 is now being kind of like up here-ish. So what does that make our range? Well, it's going to go, this got stretched down to -5 and then shifted up 4, so it's going to go from -1 is less than or equal to y is less than or equal, well, this was at 5 and then shifted up 4 more, it's 9. Looks like actually this is a little bit off. It should be -a plus k. Yeah. That way it's the vertical shift is always adding to both sides, and y is going from -a to positive a. Yeah. So this is why I don't like the formula. I'd rather just think about it to establish my boundaries. But here we go. That is the correct range, and now that formula has been corrected. Okay, let's talk about just how to plug these types of functions into our calculators. So if you've got your graphing calculator with you, get it out. No, with this button. How do I plug this in? Well, for one, if I'm given a graph down here, I want to match the units that are on that graph. This graph has degrees across the bottom. So I want my graph that I'm going to do on my calculator to be in degrees, which means I also want to make sure I'm in degree mode. All right, now I want to make my window match what I'm seeing here. So on the y-axis, I'm going from -6 to 6. On the x-axis, I'm going from some negative value all the way up to 360. So I'm going to press window. I want my x to go from, we'll say -90 up to 360. And they've got boxes every, looks like 30 degrees. So you can do 30 for your scale. And then y going from -6 to 6 with boxes every 1. Could be useful to turn the grid on. So second, zoom, grid, I like grid dot. You don't have to do this, but That way we're going to have just like some extra lines to help guide where these waves are going. All right, and now we're going to plug this in just exactly as we see it. 4 cosine 4 times cosine, 4 cosine 4 theta. The theta button's right there. It's going to still put in an x, but that's just our variable. It doesn't really matter whether we see an x or a theta here. It will graph it the same. Plus 135. Close parentheses. Yep, that looks good. Hit graph. And now if I needed to, I could sketch this graph onto this function here. I could sketch this function onto this graph. Let's try it again. Different numbers, different units. Here I see my x-axis is in radians. So how do I adjust my calculator? And it's going up to 6 pi, and it looks like it has hash marks every pi over 2. So to do this next one, I need to change into radian mode. Did it actually change? No. Then I need to change my window. Instead of going with these -90, now it's going to interpret that as -90 radians, which would be huge. We just want to go from like -pi radians up to 6 pi radians. It's going to fill in the decimal, but we'll know that that's 6 pi. With units every pi over 2 radians, and the y scale is fine. So here now, the graph looks better, but this is still graphing my old function. I want to plug in these new numbers. 4 sine x over 2 plus 5 pi over 4. So 4 sine x over 2 plus 5 pi over 4. I probably needed to close that parentheses, but it's looking okay. All right, so that's going to really help you on that worksheet. And we'll call that good for this video. Have a good rest of your day.